Okay, in our last lecture video, we talked about Diels-Alder reactions, where we take a diene and react with an alkene and end up forming a cyclohexene. And we talked about the two of the three rules that we have to follow in writing the products of Diels-Alder reactions. The first is that the diene had to be in the cis conformation, which means that the diene had to look like this in this conformation. So here is an example of that. And then the second was that whatever the stereochemistry of the alkene was, that is preserved in the final product. So if the alkene is cis, then those two groups end up being cis in the cyclohexene ring. And if they were trans, then those two products would be trans. So what we need to now deal with is the third rule, which says that when a cyclic diene and a substituted alkene are reacted, and it has to be a cis substituted alkene, the endo product is the major product that's formed in this reaction. So we got a lot to deal with here. Number one, the cyclic diene. So what does that mean? Well, let's say that I have this molecule, which is called cyclopentadiene. Cyclopentadiene is a cyclic diene where we have our four carbons of the double bond, and then we have a CH2 group attached basically to the diene, but it's a cyclopentadiene, so it's a cyclic diene. And if I react that with a cis alkene, then I'm going to get a product that has, in this case, and we'll call this 5 and 6. So carbons 5 and 6. Double bond between carbons 2 and 3. We know that the CN groups are going to be cis, right? And this CH2 then is going to be attached both to carbon 1 and to carbon 4. And so what I'm going to end up doing is I'm going to end up forming a bicyclic molecule. So if we go back to first semester, if you remember, we had these types of bicyclic molecules, except this is a bicyclic alkene. And so in this case, the CH2 group, this is our CH2 group of that bicyclic system. And so if we want to, we can imagine, okay, we're up here looking down on that, which means this CH2 is going to be pointing towards us in bold. The question is, we know from the rules that these two CN groups have to be cis. But the question is, are they in these positions or are they in these positions? Are they in either one of those two positions? And the quantum mechanical rules say that they will always form what is called the endo product. Okay, so let's look at that endo product and then we'll determine where the CN groups go. So here is that reaction, only with the CO2H groups, and still cis with our CH2 group here. And here's our CH2 group looking at it from the side. So what I had written was this. I had written that molecule. If we look at that from the side, it looks like this. Okay? And the question is, where do the CO2H groups go since they're cis? And they can go into either of these two positions. Now, if you look at these and you go, that looks like it's an equatorial position. Yes, it is. Oh, those look like they're axial positions. Yes, they are. Because this bridge kind of pins this ring into a boat cyclohexane. So we still have our axial and our equatorial positions. So the question is, where do the groups go? And they go actually in A. A is the only product that's formed. Although I always thought, to be honest with you, that this was one of the quantum mechanical rules that if you violate, the world ends, which isn't that far away given all of our current situations, but I digress. Actually, it's just a preference. So usually we form 100% of this product, but we can actually, if we raise the temperature high enough, we can actually form a little bit of this product, which I found out recently, which is kind of interesting. I always thought you only form this set of products. Now this is called the endo product. And this product over here is called the exo product. Now the endo and the exo have very specific definitions. And the very specific definition is that what I've highlighted sort of in blue here in the bold is the idea that sometimes it's hard to know which of these propellers, and if we go back to first semester when we were naming bicyclics, we had this idea of the propellers. Well, the reference is always the one with the double bond. So if you looked at that molecule and then where the groups are, the other group is automatically going to be like a bridge. So if the two groups are anti in terms of now this sort of this plane right here, if they are opposite, that is called the exo product. And if we think about this sort of this square being a plane, if they are cis or sin and cis and anti and trans are just different ways to describe the same phenomenon. Now I won't get into technical details at this point. If those two groups are then sin to where the group of the double bond is, then that's endo and exo. I kind of use the idea of using this term endo and exo with what you know. So if you take in biology, what is an exoskeleton? An exoskeleton means it's a skeleton on the outside, whereas the endoskeleton that we have is on the inside. So what I like to think about with this molecule is if I have it oriented where these are my groups are over here, I kind of think of orienting this molecule so that I have like a cylinder. And the cylinder with the double bond and then the groups at the edges of the cylinder. And so if the groups are pointing outside of the cylinder, that makes them exo. If the groups are sort of inside the cylinder, then I think of that as being endo. So that's sort of the way I think about endo and exo, kind of relating it to what those, sort of what our English definitions of what those words mean are. So endo just basically means that both the groups are in the axial position. And quantum mechanically, that is the favored product of this reaction. So you get the endo product as the major product of that reaction. So going back to the original molecule here that we had drawn, the endo product means that, just jumping back here for a moment, means that relative to this bridge, these two groups are basically, if this is pointing up towards you, these are pointing away from you. So what that means is, that means if the bridge is bold, those two groups are dashed. That is the endo product. Whereas if the bridge is bold and the substituents are bold, then that's the exo product. So it doesn't matter to me whether you write the product in this case, if we wrote it like this with our CO2H groups, which are carboxylic acid groups. You could write it this way or you could write it this way. Either one is fine with me. But quantum mechanically, you get the exo product. Or sorry, you don't get the exo product. You get only the endo product. That is the major product. And for the most part, at room temperature, it is the exclusive product. Although it is possible to make the exo product if you go to a high enough temperature. Okay. So one of the reasons why this reaction turns out to be important is there's a couple of features with a cyclic alkene. And cyclic alkenes tend to react very quickly. So if I take, for instance, if I made a cyclohexadiene and I was to react it with our cis alkene, again I would go carbon 1, 2, 3, and 4, and then 5 and 6. So I'm going to form a 6-membered ring. Carbons 1, 2, 3, 4, and then 5 and 6. Double bond between carbons 2 and 3. Now what I have is I have two CH2 groups. So that means bold wedge, CH2, CH2, bold wedge. And then the CN groups would have to go on a dashed wedge to form the endo product. Okay. Now, cyclic dienes react very quick because they are in their S-cis conformation. That is, being in a ring forces the double bonds to be in S-cis, which makes these reactions go very fast. So this structure, actually, this would be one of, and we saw these back in first semester, this would actually be the molecule that we would make. We would have our CN there and our CN there, and then our hydrogens would be in our equatorial positions. So this was a bicyclic compound that we saw before. So Diels-Alder reactions then, if you have a cyclic diene and a cis alkene, you get the endo product. Now, I should say, I'll put an oxygen there. What happens if you had the trans product or trans alkene? Well, what I would end up doing is I would end up forming my 6-membered ring. 1, 2, 3, 4, 5, and 6. Double bond between carbons 2 and 3. Carbon 1 and 4 would have the oxygen in this case. And in this case, now 5 and 6 would be, they have to be trans, so a bold wedge and a dashed wedge. That product does not have a name. It's not endo, it's not exo. So you only get the endo product exclusively when you react the cis alkene, because that's the only way you get the endo product. This is not endo, it's not exo, it doesn't have a name. And so it's only when the alkene is cis do you get the endo product being formed. Okay, so again, this molecule is called furan, and furan actually reacts very rapidly in this Diels-Alder reaction. So I want to talk about two other aspects of this, and that is the idea that these Diels-Alder reactions turn out to be very important reactions to make things like terpenes that are found in essential oils and fragrances. And I'll just show you an example of that. So here is an example of a molecule called isoprene. And it's a diene. And it can actually react with itself. So if you think about this isoprene molecule looking like this, the diene of one isoprene could react with the alkene of another isoprene. So the pair of electrons, if I write out my bonds, I go 1, 2, 3, 4, and then 5 and 6. So I could do this and this and this. So then I can form my 6-membered ring, which the numbering is going to kind of be a little bit askew. So carbon 1, carbon 2, 3, 4, and then 5 and 6. So double bond goes between carbons 2 and 3. On carbon 3, there's a methyl group. And then on carbon 5 in this case, I've got that. So this molecule is called limonene. And it's exactly like it sounds. Limonene is a molecule that is in citrus peel oils. If you have a soda, that's a component of the citrus flavorings. It's in a lot of different essential oils that are used as the basis for fragrances. Plants are very good at doing these Diels-Alder reactions to form these types of molecules, including some of the bicyclic compounds that we see here. So some of these bicyclic compounds are also components of essential oils and fragrances. So plants are very, very good at doing Diels-Alder reactions to form these molecules. And so, most people don't really care about plant chemistry, but they're doing basic organic reactions to form then the fragrances and other materials that have a particular odor or particular fragrance. We actually generate a chiral center here, and one enantiomer has one type of smell and the other one has another type of smell, which means that the receptors in our nose are chiral and able to differentiate between those two enantiomers. So just point out the idea that these Diels-Alder reactions occur in plant materials quite a bit. Now, the other thing that I'm going to point out here is the idea that in a Diels-Alder reaction, there is a way to optimize this Diels-Alder reaction to make it go as quickly as possible. And that is, if I go to the Top Hat textbook here, in chapter 19, it talks about the effect of substituents on the rate of reaction. And what you can see in this description is that the reaction goes fastest. In other words, lower temperature and faster reaction rates of a Diels-Alder reaction can be achieved if the diene is electron rich and the dienophile, which means the alkene, is electron poor. So we want the diene to be electron rich and the alkene to be electron poor. So we want this diene to be electron rich and this to be electron poor. Now, the molecules that I've written in some of the examples that I've done here are actually set up that way. When you have a methyl group on a diene, this is actually causing this diene to be electron rich. Now, what we're talking about in terms of being electron rich means that I put a group on here that pushes electron density into that double bond, making it electron rich. Well, we already know that an alkyl group pushes electron density into the double bond. Take a breath. That's why more substituted double bonds are more stable, right? Because the carbon attached to the hydrogen is slightly positive. At the expense of the carbon becomes slightly negative and has that extra electron density to push. So alkyl groups are electron donating and they push electron density into the diene. Now this carbonyl group that's attached to the alkene that wants to be electron poor will actually pull electron density out of the double bond. And we'll talk about the mechanism of that in the next chapter, so I don't want to really jump ahead here, but let me just take something simple and say, let's say I put 2 bromines onto that alkene. If I put 2 bromines onto that alkene, what would happen is that the bromines being more electronegative would pull electron density out of the double bond, and that's what would make it electron poor. So in this case, the way to push electron density that we know of right now is add an alkyl group that will then cause the carbon to have slight negative charge, which would then push electron density, making it electron rich. Maybe put a halogen on the double bond that's going to withdraw electron density from its electronegativity difference, and that would make the double bond electron poor. We'll get into much more details of this because in our reactions of benzene rings, we need to talk about pushing and withdrawing electron density and the strengths of those effects, and what groups are stronger at pushing and which groups are stronger at withdrawing. So we'll get into that in the next chapter. But just so you're aware, when Top Hat says that you need an electron-rich diene and an electron-poor alkene, that's what they're talking about. And then they get into electron donating effects by induction. We'll talk about that. And then the electron donation by resonance. We'll actually get into that topic in the next chapter. So I'm going to hold off on that for the moment. Okay, so those are our reactions of conjugated alkenes. 1,2,1,4 addition and Diels-Alder. So now let's move on and talk about the most conjugated system that we can get. And that is benzene. The benzene, or what is called an aromatic ring. So in this case, the aromatic term I will talk about has dual meanings. Benzene ring compounds tend to have a particular, not fragrance, but they have an odor, so they could be called aromatic that way. But aromaticity is going to mean something else in a few minutes. It's going to mean superstability. So the benzene ring is the ultimate conjugated system, alternating single and double bonds in a 6-membered ring. Perfect. The perfect conjugation. And it turns out that all of the double and single bonds have exactly the same length because of the resonance structures that we can draw. So it's a perfect hexagon. And it's perfectly flat because all of these carbons are sp2 hybridized. And so what that means is it makes a perfectly flat molecule, perfectly planar molecule. So in terms of resonance, there's 2 different resonance structures that we could draw. We could take this pair of electrons, move it here, take this pair of electrons, move it here, take this pair of electrons, move it there. So we can have 2 different kinds of benzene rings that are both conjugated but have different absolute positions of the double and single bonds. And these resonance structures are what are called Kekulé structures of benzene. And they are named for August Kekulé, who was the person that proposed those resonance structures. He didn't even know they were resonance structures. He just proposed the structure of benzene. And so the story goes that Kekulé knew that benzene molecular formula was C6H6, and he couldn't figure out how to arrange the atoms to get that structure. And in one of the online quiz questions from this, there's a question that shows you the different kinds of structures that were proposed for benzene. And I actually, the oldest organic textbook that I have is early 1900s, maybe late 1800s. And at that time, they had just pretty much settled on the fact that Kekulé's structure was correct, which is these ones. But they had all sorts of weird things. I'll just show you one, and then you'll see the other ones, and you'll see them in the textbook. They thought that all the carbons were bonded together, and so they had that. But ultimately, at that point, the textbook actually has good arguments for Kekulé and good arguments against these. So it was right at that end, right at the beginning, or right at the end, I guess, of the debate, that everybody was willing to say, okay, the Kekulé structures are the true structures of the benzene ring. But what Kekulé did was he was thinking about this, and the legend is that he was imbibing in some adult beverages by the fireplace, thinking about this problem, and then he fell asleep. And he had his dream of snakes, where the snake wrapped around and grabbed its tail. And then when he woke up, I'm sure he said something like, okay, benzene is a cyclic ring. And you'll sometimes see the snake wrapping around and grabbing its tail as an alchemical symbol, or some sort of new wave type, or new religion, or new whatever type symbol. But it comes from Kekulé's dream of snakes. So he proposed that these were the two resonance structures of benzene, even though he didn't know what a resonance structure is. And quite honestly, they didn't quite know that benzene needed to have 4 bonds. They did, but they didn't know why. So these are the Kekulé structures. And initially, when Kekulé proposed these structures, people thought that these two structures were constantly flipping back and forth. Right? When we start with resonance theory in the beginning of the Organic 1 class, we say that what's the true structure of any set of resonance structures? It's the resonance hybrid. And so at some point, people thought that the Kekulé structures were constantly flipping back and forth. I'll just give you an example. They thought that for instance, this molecule, they thought, well, okay, if this is constantly flipping back and forth between these two resonance structures, shouldn't these be two different structures? Because after all, the two methyl groups attached to these carbons, and in one case is a single bond, and in another case is a double bond, shouldn't that give us two different molecules? And what they found was they could never get two different molecules because it isn't. It's one molecule with two resonance structures. The true structure is the resonance hybrid. So what you see is the resonance hybrid would have partial double bonds all the way around the ring. Organic chemists, for the most part, don't like math, and we're lazy, so we abbreviate that as a circle. I don't. I've gotten out of the habit of not putting the circle in, but that's where the circle comes from for a benzene ring. It comes from this resonance hybrid. And all of these carbon-carbon bonds are perfect averages of a single and a double bond. So 1.54, as we saw in one of the previous lecture videos, the single bond 1.54, double bond 1.33. I think I had 1.34 before. The perfect bond distance here is 1.40. And so that's what a benzene ring turns out to be. All of the p orbitals of the sp2 hybridized orbitals are parallel to each other, which means that we have continuous overlap, top and bottom. So that means the benzene ring is flat. The electrons, in this case, are mushroom shaped. You could almost think of it as donuts as well. And that's where the electron density is. That's where the delta, the red in these types of plots means there's a negative charge there. So that's what benzene looks like, is it's perfectly shaped as a hexagon. Now, benzene is an aromatic compound. All of these compounds that we're going to talk about that have benzene rings could be considered aromatic. What does aromatic mean? It means super stability. Benzene itself, having those 3 double bonds, will not react with the reagents that normally react with double bonds. So for instance, we know that if we took a double bond and reacted it with Br2, we would add 2 Brs across a double bond, 100% trans. Well, if you add Br2 to benzene ring, to benzene, nothing happens. If you add CaMNO4, which should at least add maybe 2 OHs or cleave the double bond, CaMNO4 just sits there. It doesn't do anything to benzene. Sulfuric acid that should basically add H plus H2O doesn't do anything. So benzene has this super, what I call super stability, which we call aromaticity. It's aromatic. Now, can we make benzene ring react? Oh, yes. But it's going to take a little bit of work because it is so super stable. So here's an energy coordinate diagram that shows you how we get at that. And in this case, in one of the previous lecture videos, I talked about, okay, what if we do hydrogenation and these reactions all turn out to be exothermic? If I take cyclohexene and I measure its heat of hydrogenation, it's 120. And I think it might be 120 kilojoules per mole or kilocalories per mole. The energy unit's irrelevant. So you get 120 energy units to form the cyclohexane. If we take the conjugated system, we should get 240, right? Because 120 per double bond, but we only get 231, which means that we've got a difference of 9 because the system here is conjugated, and so therefore it's 9 energy units more stable because of the conjugation. So this would correspond to maybe something like this, where we had isolated double bonds and we were hydrogenating them. That should give us a 240. So if you say benzene doesn't have anything, it's not conjugated, then you should get 3 times 120 and you should get 360. But when we actually measure the heat of hydrogenation of benzene, we only get 208, which puts it here, which means that benzene is more stable than the conjugated diene. And this 152 here is sometimes called what is called the resonance energy. It's the stabilization of being aromatic. And so benzene is a very stable molecule. It has a lower exothermic heat of hydrogenation. So that means that it won't react like double bonds will, or it's going to take a little bit of work because it's so stable. Okay? And we'll come back to that. We'll come back to reactions of benzene in the next series of lecture videos. I want to throw in just a couple of practical things. We're going to use the terms ortho, meta, and para a lot. So let me introduce what they mean. Ortho, meta, and para refer to a substitution pattern of 2 groups on a benzene ring. So if I have this Y group, if I put a group at the 1,2, so it's 1,2 disubstituted, that's called ortho. If that benzene was 1,3 disubstituted, it would be called meta disubstituted. And if it was 1,4, it would be called para. So ortho, meta, and para. And so we want to remember these substitution patterns because we're going to use those in the future as we begin to do reactions of substituted benzenes. So I just introduced that now, and we'll come back to that later. Okay. But now let's talk a little bit about aromaticity and the idea of molecules being super stable. So what we saw with benzene was that it was planar. Well, other molecules that are aromatic, toxic, and planar are polyaromatic hydrocarbons, which are sometimes called PAHs. And here are some examples of PAHs. Naphthalene, anthracene, benzopyrene. Biphenyl is not really a polyaromatic hydrocarbon because it isn't planar, but its polychlorinated biphenyl derivative is very toxic, and that's PCB. And PCBs came into fame, or I guess infamy, back in the 70s in Buffalo with the place where they found the old transformer oils that had been buried in the ground. Love Canal, if you're from the Buffalo area, if you're familiar with that, those were PCBs that were used in transformers, and they were found to be very toxic, and they shouldn't have been, put in a landfill. So those are polychlorinated biphenyls. Benzopyrene you can actually detect in cigarette smoke, or sometimes these PAHs are, they say, if you char a vegetable or if you char a meat, the char has all of these PAHs in it, and so it's going to be carcinogenic. Tasty, and maybe carcinogenic. We're more concerned about the PAHs that you would breathe in your lungs if you were smoking a cigarette, or even, I believe people have found that these aromatic compounds can be formed in the e-cigs when you're vaping. So these are all PAHs, and they're all planar. The PCB not so much, and biphenyl not as much, and we'll talk about why in the future. But certainly these benzopyrene and anthracene. So what is their mechanism of carcinogenesis? I believe, and I took one semester of biology in college, second semester senior year, while I was taking biochemistry. So normally I would say I know this much biology and my fingers would be nearly touching. So take that with a grain of salt, but there are these grooves in your DNA, and so those molecules can kind of stick in those grooves. I believe that's called intercalation. And I might be sandbagging you that I know a little bit more biochemistry than I'm putting on. So the idea is that those planar molecules can interact with DNA in a not so good way. So aromaticity means superstability. So benzene and PAHs are super stable. They will not react with bromine or sulfuric acid or KMNO4. They're just like benzene. So again, aromatic means super stable. So for a molecule to be aromatic, to be super stable, it has to fulfill two criteria. Number one, all the atoms in the ring must be sp2 hybridized. And as a result of that, the molecule then is planar. It also must contain a total number of pi electrons that fits the rule of 4n plus 2, where n equals an integer or 0. And that is what is called Huckel's rule, or Huckel's rule. So 4n plus 2 is a formula to generate the number of pi electrons that would make a system aromatic. So if we use this 4n plus 2 rule, basically we would have 2, 6, 10, 14, 18, etc. And if a molecule, and we'll do some examples here, contains 2, 6, 10, 14, or 18 pi electrons, then it fulfills Huckel's rule. And if all of the atoms in the ring are sp2 hybridized, then it's going to be aromatic, which means that it's going to be super stable and very unreactive. So let's play the game, aromatic or not. Okay, so can you look at any of these molecules and say that's definitely aromatic? And what I would say is let's start with this one, because this one looks like the anthracene that I saw earlier. It is anthracene from earlier. So first, are all of the carbons in the rings, are all those carbon atoms sp2 hybridized? Yes. Because remember, a carbon-carbon double bond has to be sp2 hybridized. So check on criteria number 1. How many total pi electrons do we have? Well, in each double bond, we have 2 pi electrons. So we got 2, 4, 6, 8, 10, 12, 14. We've got a grand total of 14 pi electrons. Does that meet the 4n plus 2 rule, where n is an integer? Yes, because if n was 3, we would get the number 14. So this is aromatic. Okay. Now, what about the rest of them? Well, let's go through. This is not sp2 hybridized, not aromatic. Let's come back to this one. sp2 hybridized, not aromatic. Not sp2 hybridized, not aromatic. Not sp2 hybridized, sp3 hybridized, not aromatic. Not sp2 hybridized, not aromatic. So none of those are aromatic because they all contain sp3 hybridized carbons in the ring. Let's deal with these two guys though. The stop sign shaped cyclooctatetraene and cyclobutadiene. Okay. Now, these all have sp2 hybridized atoms in their rings. So check on criteria number 1. How many total pi electrons do we have here? We've got 4. How many do we have here? 8. Well, those are not 4n plus 2. Those are 4n numbers of electrons. And molecules that are planar and have 4n numbers of pi electrons are called anti-aromatic. And so what does anti-aromatic means? Well, if aromatic means super stable, anti-aromatic means super unstable. So whenever you say to a chemist, you know what, this molecule is so unstable that I can't make it, you know what people try and do? They try and make it. So I know for a fact that this molecule right here has been made, but it exists for like a split second, long enough for them to study it, and what they actually found was that it's sort of like this. It's kind of a parallelogram with a long single bond and then a short double bond. But it only exists for a split second, enough for them to get the structure of it, but it is very unstable. I don't know about cyclooctatetraene. I don't know if anybody's done that. I think in this case, if you did make it, it wouldn't be planar. It would kind of pucker and would be not cyclohexane puckering, but it wouldn't be planar. But I know for a fact this one has this kind of structure. So molecules can be aromatic if they have 4n plus 2 pi electrons and they are planar. They will be anti-aromatic. Now, a molecule will not choose to be anti-aromatic, it would just choose to be not aromatic. And I'll talk about the criteria for that in a minute. So 1 aromatic, 4 non-aromatics, 2 anti-aromatics in this list. Okay. Now, ions can be aromatic. They can fit the rule of being all sp2 hybridized in the ring and having a 4n plus 2 number of pi electrons. So let's deal with the tropylium ion. In mass spec fragmentation, we oftentimes see the tropylium ion formed. Benzene ring does a ring expansion on a benzylic carbocation and forms a tropylium ion. Tropylium ions tend to be more stable than your run-of-the-mill carbocations because they have actually lots of resonance structures. So you could take this pair of electrons and move it here, and then move around the ring to form different carbocations, and eventually all of these positive charges will end up, you'll have a resonance structure with a positive charge on all the carbons. But this tropylium ion, a carbocation must be sp2 hybridized. So all these carbons in this 7-membered ring are sp2 hybridized, and we have 2, 4, 6 pi electrons. This would be an example of an aromatic carbocation, and it's called the tropylium ion. And because of the resonance structures you can draw, it usually has a circle in it. This cyclopropenyl carbocation has this carbon being, well, first of all, it's got to be a plane because there's only 3 atoms and 3 points define a plane, so that makes the molecule planar. This carbocations, again, must be sp2 hybridized, and in this case it's got 2 pi electrons, so this would be aromatic as well. Now, what does it mean? Does it mean that this carbocation is so super stable that it won't react with an anion or a nucleophile? No. What it means is that this carbocation is much, much, much more stable than your run-of-the-mill secondary allylic carbocation because it is aromatic. It fits the rules of aromaticity. Okay. And in mass spectrometry, what that means is this is very easily formed and is very stable in the gas phase. Now this carbanion, this is a cyclopentadienyl anion. What I did here was I took a cyclopentadiene and I lost an H plus to form this anion. Now we haven't talked about carbanions, right? We haven't talked about a carbanion with a negative charge because carbanions are funny. Carbanions can either be, they can choose to be sp3 or they can be sp2. If they're sp3 hybridized, that means they're just basically tetrahedral with the pair of electrons in an sp3 hybrid orbital. But they can choose to be sp2 hybridized where the pair of electrons would go in the empty p, or not in, it's not empty p orbital, it's a p orbital. It's not empty, it's got a pair of electrons in it. So carbanions can actually choose to either be sp3 or sp2. And this is where I'm going to give these molecules kind of human characteristics. So in this case, this carbanion, this carbon, could be sp3 or it could be sp2. And what it's going to say is, it's going to say, you know what? How many pi electrons do I have? And it has 2, 4. It's got 4 pi electrons right now. And what it says is, well, you know, I could become super stable if I put this pair of electrons into that p orbital such that I become planar, and here's my 2 and 4 pi electrons. If this carbon, the molecule says, you know what, if I make this carbon sp2 hybridized, that pair of electrons is going to go in that p orbital. I'm going to become planar, and now how many pi electrons do I have? I've got 6 pi electrons. I'm aromatic. I'm super stable. And so the molecule will do that. If, on the other hand, putting that pair of electrons into the p orbital doesn't get you 4n plus 2 pi electrons, or heaven forbid it gets you 4n numbers of pi electrons, it won't do it. It'll just say, you know what, I'm going to stay sp3 hybridized, because if I was to do this and have 4n numbers of pi electrons, then what happens? Then I become super unstable, and the molecule's going to say, you know what, I'm just going to become sp3 hybridized, so that way I automatically am non-aromatic, which is more stable than being super unstable and being anti-aromatic. And I'll show you an example of that in a few minutes. So carbanions could go either way. They could be sp3, they could be sp2. They're going to choose whatever will make them the most stable. So if it makes the molecule planar, throws in the pair of electrons to form 4n plus 2, it will do that. If it can't, or if that makes it anti-aromatic, then it'll just stay sp3 hybridized. Okay. Again, the idea here is that this carbanion, being aromatic, is much more stable than a normal run-of-the-mill allylic carbanion. And we'll talk about those later on. Okay, so you can also have heterocyclic aromatic compounds that have nitrogen or oxygen or sulfur in the ring that will make them aromatic. So here's our pyridine. Where did we see pyridine last? In our PCC reagent that oxidized a primary alcohol to an aldehyde. Pyridine is a very strong base. We'll talk about that, why that's the case. But pyridine is aromatic. So in this case, this nitrogen is sp2 hybridized because it's got a double bond and it's got the single bond and the lone pair. Remember that sp2 means what? It means 3 hybrid orbitals. 3 hybrid orbitals, and how do we count hybrid orbitals? Hybrid orbitals come from the number of lone pairs plus the number of sigma bonds. So 1, 2 sigma bond, 1 lone pair, 3 hybrid orbitals, sp2 hybridized. So this nitrogen is sp2 hybridized, which means all the atoms are hybridized. sp2, we've got 2, 4, 6 pi electrons, therefore this molecule is aromatic. And what that means is it's super stable, but this lone pair of electrons on this nitrogen could be used. They're going to make that nitrogen a basic nitrogen, and means that it could be used to bond an H+. Okay. Now, pyrrole is aromatic, but it has a lone pair on its nitrogen that will not be able to bond an H+. You might say, well, why? Well, so pyrrole, what's its hybridization? Its hybridization is it's got 1, 2, 3 sigma bonds and a lone pair. So it's sp3 hybridized. But nitrogens that are sp3 hybridized, or oxygens or sulfur that are sp3 hybridized, can do the following. They can decide that nitrogen can decide, you know what, I'm going to become sp2 hybridized, and I'm going to throw that lone pair into the unhybridized p orbital. And when it does that, what happens? Well, all of the ring atoms become sp2 hybridized for this pyridine, or for this pyrrole. And then, if you think about these pi bonds, each having then 2, 4, if this nitrogen says, just like the C minus in the example before with the cyclopentadienyl anion, if the nitrogen says, you know what, I'm going to become sp2 hybridized, I'm going to throw my pair of electrons into an unhybridized p orbital, I'm going to then make it available so that now I've got 6 pi electrons, now I'm going to become super stable and aromatic. And that's exactly what that nitrogen does. Now, anytime the lone pairs are part of the pi system, they are not available. They are not available to bond an H+. And so therefore this nitrogen is not basic, because its lone pair is tied up in the aromatic system. For pyridine, its lone pair was outside of the aromatic system, so it was basic. So if we go with furan, which we saw with Diels-Alders, we could use that molecule in a Diels-Alder reaction. Oxygen is basically the same. It could say, well, I could do sp3 or I could do sp2. So it consults with the rest of the molecule and says, well, you know, we've got 4 pi electrons. If you become sp2 hybridized, then that means we'll become planar. Well, all of our ring atoms will be sp2 hybridized. And then if you do that, then 2 of your pairs of your 1 pair of electrons, your 2 electrons will be in the unhybridized p orbital. And now all of a sudden we've got 6 pi electrons, and so now we become aromatic. So nitrogen and oxygen and a C minus can all choose to be sp2 or sp3. They're going to choose whichever one makes the molecule the most stable. This lone pair on the oxygen could not be used to bond an H+, but this oxygen could. So this could bond an H+, and so for that oxygen is therefore basic. Okay, so there are some times when these nitrogen atoms will choose to be sp2, and that's when the molecule becomes, all the ring atoms become sp2 hybridized, criteria number 1, and then we get a grand total of 6 or 4n plus 2 numbers of pi electrons. So let me just look at one more example here. And the one more example I will look at is the following, once I get rid of these boxes. So let's say that I had this molecule. Because this is my favorite sort of trick question molecule. And I would say, this molecule, is it aromatic, not aromatic, or anti-aromatic? And so this molecule has 2 atoms that could choose to become either sp2 or they could become sp3. So in order for this molecule to become aromatic, the first criteria is they all have to be sp2. And so let's just say the molecule says, hey, let's go ahead and do that. So let's go ahead and take my nitrogen and go ahead and put that pair of electrons into the p orbital. And the oxygen says, okay, I'll put my pair of electrons into the p orbital. and we will become sp2, both sp2 hybridized, so that we can check off criteria number 1, that all of the ring atoms are sp2 hybridized. And it could do that. Okay, it could very easily do that. This would be in this pair of electrons would be in the sp2 hybridized orbital. This would be in the unhybridized p. This pair of electrons for the nitrogen would also be in the unhybridized p. So let's say the molecule says, you know what, let's fulfill criteria number 1 and make all of the ring atoms sp2 hybridized. How many total pi electrons would I have? I would have 2, 4, 6, 8. I would have 8 pi electrons. What does that mean? That means if the molecule decided to do that, it would then fit and become anti-aromatic. Well, the molecule's going to go, wait, hold on for a second here. If I do that, then I'm going to become super unstable. Well, it's one thing if I do it to become super stable, but I'm not going to choose to do that to become super unstable. And so basically, this molecule, these nitrogen and oxygens, they're going to say, you know what, one of you two could be sp2 to sort of make a conjugated system, but both of you cannot. Which one would it be? That's an interesting question that we won't get into now. But the key thing is, this molecule is going to say, no, I'm not going to, both these atoms are not going to become sp2 hybridized, because if I did that, I would become anti-aromatic. And so instead, it's going to just say, you know what, I'll stay as non-aromatic. Because if I can't be super stable, at least don't become super unstable. Just stay in the middle. Okay? So when you're looking at problems, when you're trying to determine aromatic, non-aromatic, and anti-aromatic, you have to see if all the ring atoms are sp2 hybridized, and if they are, then count up the number of pi electrons. For atoms like oxygen, nitrogen, a C minus, which means that C has a lone pair on it, then 3 bonds and a lone pair. Those could choose to be sp2 or sp3. What's going to dictate that? Whether or not that pair of electrons is going to make the system aromatic. If it will, it'll go sp2 and make the system aromatic. If it doesn't help, or if it makes it anti-aromatic, it's just going to say, you know what, I'll be sp3 and I'll be non-aromatic, because at least then I won't be super unstable. Okay? So that's kind of the basics of aromaticity. And if the lone pair of electrons on the oxygen or nitrogen is tied up in the pi system, making it aromatic, that nitrogen is not basic and cannot take a proton. Okay? So that's our introduction into benzene and aromatic and aromaticity. In the next lecture video, we're going to talk about the reactions that occur out on chains that are attached to a benzene ring, our benzene side chain reactions. And then we'll talk about actually adding things to the benzene ring. So that'll happen in the next couple of lecture videos. Okay.